Hello everyone, I am still Spencer Hall, and I also still hope to graduate. Today we're going to be discussing feedback loops. So let's begin. What exactly is a feedback loop? It is one of our bodies and also a given population's best types of regulation. Regulation being quite important because if we did not have these types of regulations such as feedback loops, we'll be overrun with, for example, hormones that we do not need or molecules. And these, in many different ways, could just lead to rapid death. So let's discuss the two different types first. There's negative and positive feedback loops. The idea behind the negative feedback loop is that as something is produced more of, or as something happens more, it causes the exact opposite effect later on. This might sound a little confusing, but let me give an example of this. If we have an enzyme, looks like this, say. This is a little site where a substrate can fit. And a substrate would just be any molecule that could be, I don't know, floating through your blood, for example. But it could also be in need of changing, readjustment. So I'm going to draw a circle substrate right now. This circle substrate could come to the enzyme. And this enzyme has the ability to change this circle and a few of its properties into something different. Say that now a square came out. The enzyme returns back to its original position in many different ways and is able to continue getting more circles. So this works, right? But if all we ever did was produce circles which are turned into squares, then you'd have a lot of squares unless you have some ability to get rid of it. Our bodies are way smarter than that. So let's call this enzyme A. And A does not operate alone. Rarely will you see an enzyme do that. Instead, you'll be likely to have A, which produces something that B can use, which produces something that C can use, and this can go much farther than what I'm doing right now, but we'll just go to D right now. So these products can come, and I guess it could be other ones, and have an impact on our A enzyme. So there's two different types. One would be to somehow cause A to produce more, but for negative feedbacks, we would have inhibition of enzyme A. And this could be, let's say that D produces a star shape. So circle, squares go to B, it goes to C's. Maybe they play with triangles, I don't know. And then goes to these stars. Well, this star has a few different methods to sort of shut off or close down A. The star could come in and fill it in here. It's called competitive inhibition. If a star is there, the circle can definitely not fit in there. However, it could also attach to something called an allosteric site at the back. You have several different kinds of inhibition, or in other words, ways of shutting off an enzyme. You have the non-competitive, you have uncompetitive. I already described competitive over here as well. And then there's also like a type of suicide one where it attaches A and completely and permanently closes down this enzyme. In which case now you have to create some more of that as well. But beside the point, this product of D has been able to inhibit A. And as there's less of A, we end up using, or less of A's products, it'll be less likely for B to work to get the new products, and then C, and then D, which interestingly enough, now means that there's less things to stop A from doing its work. And then A can work better, which means that more B will be produced, more C will be produced, or their products will, and then D, which means that A can be inhibited more. As you see, this kind of continues to go in a circle, increasing and decreasing. The idea, though, is regulation, as I stated earlier. And that means this will be around a perfect amount that is needed. This is a very smart system our bodies have. But negative is only one type. Positive is another. So I'm going to draw here a baby. This baby is in, I don't know, that's like a uterus. And then you have a cervix here. The idea is as the baby continues to grow, it pushes against this wall, this cervix. And as that happens, a signal, boop, 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 is sent up to the brain. That's going to have to, okay, that's not really a brain, but it's a brain. And the brain says, oh, this signal means I'm supposed to release a certain type of hormone. It's called oxytocin. Main thing to know about it right now, though, is that it causes this to contract. And when that does happen, well, the baby pushes up against it, right? Interestingly enough, that is exactly what spawned the signal in the first place. So what do you expect to happen again? Yet another signal. The signal goes up here and it tells the brain the exact same thing before, and yet another contraction. As you see, this will continue over and over again. You'd imagine this would endlessly happen over and over again, but as fathers and mothers know, it does not go on forever. Luckily, eventually it will stop. In this case, when the baby is able to come out. So this would be a prime example of positive feedback loop. Now, these two are not always so independent of each other. In my last little minute, let's describe how these can be working together in a very macroscopic way. Population. If you have an increase, say, in a population, what would we expect the number of births to do? And as there's more, a greater size population, more individuals who can mate and come to SVU, you would expect that the birth rate would definitely increase as well. And as births increase, given time, they'll bring about their own increase in population. That is, increase in the population, which yet again would bring about a greater number of births, and it continues on until something happens. This is a general rule. Also, generally speaking, the greater the population, the greater numbers of deaths. Now, this doesn't seem too different from this yet, does it? Well, as you have more deaths, do you expect the population to increase or decrease? And the deaths have the opposite effect. Unless you're talking about voter registration, the population does decrease with death. So as you see, you have a negative and a positive type feedback loop combination. And this happens in many other cases, and these two can individually happen in many other cases as well. But this is what we'll cover for now on feedback loops. Thank you very much.